So what's the point of a Poisson distribution? The point here is that the Poisson distribution is a good approximation to the binomial distribution when the probability of success on a trial is very small and the number of trials is large. Well, why would I want to do that? It's easier to work with the Poisson for theoretical stuff. And that's ultimately what people want, is they want to have a theory behind why all of this works. And when should I do this? Well, here's a little rule of thumb. Don't treat it as fixed, but ballpark when n is bigger than or equal to 50 and n times p is less than 5, less than or equal to 5. It doesn't really matter because it's a rule of thumb. Okay? And so in the situation when you fall into this, you could use the binomial, but again, the point of the binomial in these types of examples is that it's inconvenient. It's not easy to work with if you have to do things analytically. Now, sure, if you want to do things with software like R, then it's just a matter of crunching out a number. But we would like to have ideas that are robust. So not only are they good with computations, they're good with theory. So on the attached PDF, I've got an example. And this example says, find the probability that at most 5 defective fuses will be found in a box of 200 fuses if experience shows that 2% of all such fuses are defective. Okay, so this is a very typical type of example. They're telling us here that we've got a box of 200 fuses. We're going to assume that every fuse is independent of the other. We are going to assume that there are only 2 outcomes. The fuse is defective or it isn't. And in each case, we are going to assume that the probability that we get a defective fuse, so that would be what we call success in this problem, is 0.02. So clearly n is bigger than 200, and n times p is going to be 200 times 0.2, which is 4. So we are in a small situation here. Okay. Now, this is in the binomial setting, which is important, but the Poisson approximation should apply as well. All of those things need to be true. Remember, Poisson isn't something different from binomial. It's just an approximation to binomial. So it needs all of those settings to still hold. The question we are interested in is find the probability that at most 5 defective fuses will be present. So here, X is going to stand for the number of defective fuses in a box. And in our case, we would like to figure out this. Now, if I were to do this with binomial, right, I could use the binomial CDF. So in R, this would be P binomial. And then I would say 5, 200, 0.2. But that's fine. You can get a number and you can use that number for comparison's sake. Also realize that it would be annoying to calculate this with the formula, because what you have to do in any sort of CDF problem is add up a bunch of individual calculations like this. So a long time ago, the old timers said, well, I don't want to really use this binomial formula. It's got all these factorials and everything. It's inconvenient. Yeah, the software is easier to do, but we would like to have some other sophisticated tools, and this is what the Poisson distribution is all about. Okay, so again, if you were interested in calculating this, you have to calculate all of these individual values all the way up from 0 to 5, because it's possible that there are no defective fuses in the box. So the new tool here is that the Poisson mass function has a formula. Now, believe it or not, this formula is easier to use than the binomial one. Now here, lambda is n times p, which ends up being 4. And so in our question, we are essentially taking a sum where x is 0 going up to 5, and we are summing e to the power of negative 4, 4 to the power of x over x factorial. Now, every one of these terms has a common factor of e to the negative 4, so I could take that out. It would be 4 to the 0 over 0 factorial plus 4 to the 1 over 1 factorial, all the way down the line, 4 to the 5 over 5 factorial. Now, by definition, 0 factorial is 1 in order to make all these wonderful little formulas work out. And so we end up getting, you could use, as I've also shown on the attached sheet, you could use R to use the Poisson CDF to get a number for this. You could do it directly with a calculator, or you could use the software R to come up with this, and you would get 5 successes. Lambda is our parameter. And what you'd end up with is 0.7851338. Okay, some number. There is a fairly high probability that at most 5 fuses will be found in the box. So Poisson is meant to model rare occurring events. Not so rare that you'll never see them, but so rare enough that this kind of mathematics works. Now, from the sheet, you can look at the bar chart of the mass function for binomial versus Poisson. Now, in this particular example, I've got those bar charts up for this situation. So we've got binomial 200, 0.02 versus a Poisson bar graph of 4. They are nearly indistinguishable. And the point of all of that is that Poisson is a good approximation, a very good approximation to binomial in this case. And that really is the utility here of Poisson. It gives you an alternate, probably quicker way of working with things. Now, admittedly, when you've got software like R, there's no effective difference, and you could just use binomial whenever you want. But the point of the story is to learn that Poisson is another option, and it has theoretical benefits. In the next video, I'm going to show you one of the main uses of the Poisson mass function.